Morning, everybody. Morning. This is it. The last unit of this course. You've made it? Maybe not yet. So what do we need to do in the last, 4 weeks of classes that is it really only 4? This next week? Yeah. And then Thanksgiving? No, 3 weeks of classes. It's only 3 weeks of classes left. Okay. I need to tell you. On the Wednesday before Thanksgiving, I will be sick. I do this every year. It's my 24th year doing this. Okay, I think it is criminal, and I have evidence. That I'm not joking. That we don't have the entire week off. Every other school district in the valley has the entire Thanksgiving week off, and we don't. Yeah. We are a community college. We serve the community by making moms and dads come to school while their kids are out. I don't understand the. But anyway, to offset that, I give up one of my sick days every semester to not have class. I can't do it for Monday and Tuesday. So we will meet on Tuesday for lecture of Thanksgiving week, but Wednesday we're not having that lab. I'm going to call in sick. I will be home, hopefully not sick, but take the day to do whatever you need to. To be clear, campus is open. Your other classes might be happening. This is just a Mr. Balogh thing, right? Okay, so that Wednesday, I'll put the announcement up and all that kind of stuff. But just wanted you to know ahead of time, if you were planning something, you can say, oh, well, physics not happening that day, no lab, I can drive or do the shopping or whatever it is you want to do. Please be careful doing any kind of travel around Thanksgiving, right? It gets nuts. And please come back to me in one piece. Maybe a little bit heavier than you were before, but that's all right. And don't forget to have gratitude. Gratitude is one of the fastest ways to alleviate stress. And somehow you have to get to the point where you're grateful for a physics exam. Don't ask me how. I've never gotten to that point. So that's Thanksgiving week. Next week is not Thanksgiving. Next week's lab is more than likely going to be lecture, depending on how far I get today. But yeah, I think that's it. With the sole exception of chapter 11, back up. Teachers should never admit things like this, but I'm going to anyway, okay? With the sole exception of chapter 11 in this unit, I hate this unit. I can't stand thermodynamics. I think it's dull. I think it's boring. I think it's something that the chemists do very, very well. And so I'm voting for just let them have it. Just let chemists have thermodynamics, okay? There are physicists who disagree with me, namely just about every other one. But we have a name in physics for true thermodynamics, and it's called quantum mechanics. Okay? But the thermodynamics of what systems do and gas molecules and ideal gas law and calorimetry and all that kind of stuff, physicists stopped playing with that basically about 1890. Okay? We really haven't looked at it since because it's boring, it's stupid, anyway. So this is going to be the speed run of thermodynamics. Okay? So I'm literally going to go as fast as I can because I hate it. I'm sorry. You just need to know that up front. The other thing you need to know up front, those of you that have had chemistry, everything is going to be backwards. I'm sorry. I am a physicist, so I have to be true to my science. But you're going to be sitting there going, wait a second, in chemistry we did it. And I'll be like, yeah, no, we do it this way. Like literally minus signs will be in the wrong spot and all that kind of stuff. It comes down to chemistry's all worried about what's going on inside the gas, and physicists we're worried about what the gas is doing to everything else, right? So it's just a point of view issue, and unfortunately it totally messes up students. I so wish that chemists would just take thermodynamics and the state would stop requiring me from teaching thermodynamics in physics. So I've said my piece. I will now try to do my best to make you enthusiastic about thermodynamics. But this isn't thermodynamics. What we're going to do in chapter 11 is fluid physics. This is fluid dynamics. Fluid dynamics is fun and interesting, but I am going to go really fast in it because we need more time for the other stuff, okay? The problem in dealing with fluids, think about our physics, think about our toolboxes, right? Kinematics, Newton's laws, momentum. It all like falls apart because a fluid by definition changes its mass as it goes places, right? You dump a bucket out, the mass of your bucket is changing, right? And all of our physics kind of depends on the mass more or less staying the same. In momentum, we could embed something in, but even then it's like a momentary change in mass. It's not a continuous change in mass. So what we're going to do in fluids is we're going to switch up how we talk about our objects. Instead of mass, we're going to use density. And in physics, the volume mass density is the Greek letter rho. It's kind of a little kind of curly P. It's like, if I wanted to be really careful, it's like that, okay? But please don't confuse it with the other P, which is pressure, okay? So again, instead of mass, we're going to be inserting density into a lot of things. So we talk about the mass of a fluid, we're going to talk about its density. Density doesn't change. No matter how much of the fluid you have, like the density of water in a swimming pool versus the density of water in a sink. Which one's more dense? They're the same. Which one has more mass? Swimming pool, right? But like the density is identical. So it makes it easier for us to do calculations on what the water is going to do. Pressure instead of force. Pressure is a little bit funky, so we got to kind of talk about it real quick. Pressure really depends on area. The force is going to come into it in a little bit, but when it comes, so that's the generic definition of pressure. It's force divided by area. But in a fluid, the pressure at any point is there because of pressure being exerted on the fluid plus rho times g times h. What is this talking about? Usually what we're thinking about, again, is like a swimming pool, okay? I want to make it very clear in this picture that you are not dead. Okay, but let's say you swum down to the bottom of the swimming pool and you're laying on the bottom of the swimming pool, okay? The pressure that you experience at that depth exists because of the air pressure above the water, atmospheric pressure above the water, plus the depth of the fluid, the water that you are in. So if we were going to go calculate this pressure, right, let's say at a depth of, 2 meters, 6 feet, okay? And by the way, have you noticed the funny way that physicists spell depth? We use height. Okay, because h is just a vertical distance. We think of it in physics as the height of the water column, the height of the air column, which also happens to be its depth. But d, it's overused. Frankly, h is overused. But anyway, it is what it is, okay? So we're going to calculate this. The pressure at point number 2, down here where you are, is equal to the atmospheric pressure, usually is P naught for that one, plus rho times g times h. Atmospheric pressure, 1 atmosphere, is equal to 1.01 times 10 to the 5th pascals. The atmosphere is probably what you used in chemistry, but that's because they don't use the right units. And by the way, all of your chemistry teachers, you can go to them and say, hey, Mr. Balogh said nasty things about you. They'll go, yeah, okay. They're used to it, okay? It's all fun and games. They can use whatever unit system they want because they're consistent in their unit system. But what unit system do we use in here? SI. Okay? Chemistry doesn't use SI. They use something called CGS. But we use standard units, and the standard units of pressure are pascals. A pascal is a Newton per square meter. Okay? But an atmosphere worth of pressure is 1.01 times 10 to the 5th pascals. All right. So we can go and calculate that. But notice that pressure, the pressure you feel at the bottom of the pool, really only depends on one thing. Okay, little g, if we went to the moon or Saturn or somewhere, it would change, right? But here on Earth, little g stays the same. Density, assuming you're just in water, the density is going to be the same, right? What's the only thing that determines the pressure in a fluid? The height, the depth of the water column. Notice there's nothing in there about how the volume of water or the shape of the water. There's some lakes up here in the Sierras that have depths that are measured in hundreds of meters. Okay, very deep alpine lakes. Okay, Tenaya Lake, I think, has a depth of like 200 and something meters. If you go scuba diving in Tenaya Lake, okay, and you go down, say, 30, 40 feet underneath the surface, okay, there's a pressure there that is there because of the atmospheric pressure and the water depth. If you then go scuba diving in the ocean, but you only do it to 10 feet, which of those will you experience more pressure in? The lake or the ocean? The lake. Why the lake? It's deeper. Has nothing to do with the amount of water. Has everything to do with the height of the water column in question. That did not change. There it goes.
In that example, wouldn't the atmospheric pressure at sea level?
Yeah, it'd be different, but like air is like, well, Tenaya Lake's at 7,000. It's insignificant compared to the pressure from the water. Yeah, but you'd still win at 30 feet below the surface. Anybody know what this is? This is the Hoover Dam, okay? Lake Mead is behind Hoover Dam. It's also the place where we keep the Allspark, okay? Hoover Dam is about 800 feet top to bottom, okay? And it holds back Lake Mead, okay? Lake Mead goes back for like 100 miles. Well, it used to go back for 100 miles, climate change being what it is, okay? The level of Lake Mead is dropping, and they're finding more and more bodies. Have you guys heard about this? Okay. Bodies with blocks of concrete tied to their feet. Lake Mead's near Las Vegas. Do I need to connect the dots for you? Okay. So, yeah, getting rid of the evidence in Lake Mead, the evidence is popping back up now. Thank you, climate change. But that's a tangent. It holds back Lake Mead. The depth of the water behind the dam, let's say it's 300, 400 feet deep, okay? If we dropped a garden hose down the front of the Hoover Dam, 300-foot garden hose, okay, capped up the bottom and started filling it with water, what would the pressure at the bottom of that garden hose be compared to the pressure in the water 300 feet down on the other side of Hoover Dam? The same. This is the hard part about pressure. If you drove down 300 feet into Lake Mead and measured the pressure, and then you just took a garden hose and made it 300 feet long, capped the bottom, filled it completely with water, the pressure at the bottom of that garden hose would be exactly the same. It has nothing to do with the amount of water. It has everything to do with the depth of the water. Don't try that experiment at home, by the way, because garden hoses can't stand that pressure. So you could fill it maybe 60 feet and then it would burst. So let me see if I can't prove it to you with a video experiment, okay, that will show you that pressure is independent of shape of water, how much water. It only depends on the depth of water. Something in this video they don't do a good job of explaining is that the sensor that they are going to be using, it's going to have these lights that go up. It's exactly calibrated so that the length of the light bar is exactly equal to the depth of water. They've like designed the sensor to do that. You'll see it as it goes into the water. It will change its length and always be at the surface.
This is an electronic pressure gauge with a pressure sensor at the bottom. Blowing into the sensor through a tube increases the pressure and drives a bar graph display whose length is proportional to the pressure at the sensor. We'll use it to show how the pressure in a column of water changes with increasing depth.
See how it stays at the surface of the water?
Into this column of water. The display shows that the pressure increases in direct proportion to the depth. What will happen to the display if we tip the water column at an angle?
Okay, so what he's going to do is he's going to take that whole apparatus, the tube, the water, everything, and he's going to tilt it. Right? This isn't a quiz, but turn to your neighbor and tell them what you think is going to happen to the length of that pressure display. Is it going to go up, go down, or stay the same? Go. Okay, show of hands. How many of you say it's going to stay the same? How many of you say, oh, that's a lot. How many of you say it's going to go up, indicating a deeper amount? How many of you say it's going to go down? Shallower amount. Okay, so the majority there was it's going to stay the same. So in order for the length of it to stay the same, what else has to stay the same? The depth, the vertical height of water. If we tip this thing on its side, does the vertical height of water change? You're wrong. Let me prove it.
Tipping the column of water reduces the pressure.
Wait for it. Watch.
The length of the display is still equal to the vertical depth of water above the sensor, as shown by this line.
Pressure depends on what? Depth. And depth is what? The vertical height of the water. Not the diagonal height of the water. The vertical height. Did it matter that there wasn't water directly over that sensor? When it got tipped, was there any water right here? No. But the surface of the water right over here, the vertical difference between those 2 points is what determines pressure. Okay? Air pressure is determined by the height of the column of air above you, not how much air is around you, any of that kind of stuff. Okay? That and the density of the medium, right? You go swimming in honey, going to be a different pressure. But we also have to talk because that's weird, right? So, but air pressure changes all the time because of atmospheric differences and things like that. That is the wrong button to push. Okay. We did that. We did that. We do have to talk about gauge pressure really quickly. Gauge pressure, obviously, is what a pressure gauge measures. The problem is that what is the reading on a pressure gauge, say, when your tire is flat? What does the gauge say? Zero. Is the pressure in your tire zero? That would be a pure vacuum, like outer space type of vacuum. Okay? So when a pressure gauge reads zero, what's it trying to tell you?
It's not high enough to read.
No. Your tire's broken. Yeah. The gauge pressure, okay, is the difference between the absolute pressure, the actual pressure in the tire, and the atmospheric pressure around the tire. Pressure gauges always read a difference. They're a comparison between the ambient pressure and then the pressure in the device. So when the tire says that it needs to be filled to 44 psi, that's actually max. You don't want to go to 44 and then drive because the tire will heat up and you'll get more pressure. Typically 35 psi, right, in a tire as an average. But psi, what's psi? Pounds per square inch, okay? Got to convert that into pascals if we're doing metric system, right? Okay. So 44 psi should do 35 psi. So if the pressure gauge reads 35 psi and atmospheric pressure is about 15 pounds per square inch, it's 14.7 pounds per square inch. The actual pressure in the tire is 50. Okay? When the doctor or nurse measures your blood pressure, oh, by the way, what units are they measuring your blood pressure in? What's normal? What's a normal number? 120 over 80? That, by the way, changes over time. They've been altering the definitions for this so that less people, I guess, are in hypertension. But we consider this kind of normal, right? Systolic? Diastolic. Did I get that right? Yeah. Oh, dyslexia. Okay. Representation of
When your heart pumps.
the push of the, right? And this one, kind of the relaxation pressure, which kind of sounds weird. Yeah. Okay. So, and by looking at it and tracking it over time, you can tell whether or not arteries are healthy or the heart's not healthy or whatever. Okay. Anyway, anybody know what the unit is? I quiz my nurses every time. Good. It's millimeters of mercury. Okay. Pressure is so old as a measurement. It has so many different units, right? I've already mentioned several, right? 1 atmosphere is 1.01 times 10 to the 5 pascals, which is equal to 14.7 pounds per square inch, which is equal to, yeah, it's like 700 and, I don't have it written down. 760.
That sounds right. Let me check my calendar.
Yeah, it's 760. I can read it. Millimeters of mercury, which is equal to like 30 inches of mercury. Like, it's weird. The pressure units are weird. I'm sorry. Oh, and there's like torr, and there's a bunch of, oh my gosh, there's so many, okay? So, but that should be all the conversion factors you'd need for pressure, hopefully. You would only ever need one, but just watch out. Pressure gauges give you the difference between atmospheric and whatever's going on in the thing, okay? All right, what do we do with it? Does anybody know what this picture is? That is a automobile jack, like a lift, okay? For actually just, you pull the car over the top and it lifts up the whole car so the person working on the car doesn't have to climb underneath it. They can work at it at eye level, okay? It works under the principle of hydraulics. And this is Pascal's principle. I'll draw a schematic of a hydraulic. This isn't how actual hydraulics work. Their engineering is more complicated than this. But a hydraulic system consists of an oil-filled cylinder, okay, that has like different sized openings, different areas on either side. What Pascal said is that the pressure everywhere in a hydraulic system has to be equal. So if we take a look, say, at this is side number 1 and this is side number 2. Pascal said that in this closed system, whatever the pressure is that you exert on side 1 is equal to the pressure that you exert on side 2. It's like conservation of pressure. You can think of it like that. Okay? So if we go ahead and we throw in the definition of pressure, okay, and we solve this, we get a relationship between the forces that come out of either side. So like if you press down with force 1, the question is, how much force do you get out of side 2? They're not the same force because the areas are different. So if we said that, say, I don't know, area 1 is 10 times area 2. Something went wrong here. I didn't want to solve for F2. I wanted to solve for F1. That's what went wrong. Reverse this. F1 equals F2 times area 1 over area 2. There we go. Okay. we want to push on side 2, the small side, to get force out of the other side. So we're going to push down. There we go. Okay. I'm with you. Sort of. If this is the case, and let's say we push with, 100 pounds of force. Okay. How many pounds of force will we get out of the other side? F2 is 100. And then A1 is equal to 10 times A2. So those cancel. What's 10 times 100? 1,000. Okay. This is how a hydraulic system works. You put in small amounts of force, and you can magnify the amount of force you get out the other side by playing with area and keeping pressure the same in the system. This is why a car can be lifted up, right? A 3,000, 4,000, 5,000 pound car can be lifted up by a small amount of force that is put into a jack. Anybody that's ever had to jack up a car knows that you pay a price for this, though, right? So in my car jack, right, I wheel it under, and it's got a handle that's, about that long, okay, 1.5 meters long, right? I grab the handle. What do I have to do to get the car to go up? I got to pump it up and down, right? It like swings through like a whole meter's arc, okay? For every like meter that I move this handle, how far does the jack go? It's like hardly moves at all, right? Okay. So we pay a price in distance. We're magnifying force, but the price we pay is like how much distance we have to put into it. You can't cheat energy, you can't cheat work, right? You can just play around with force and distance and pressures and all this kind of stuff. So you have to pump for 6 or 7 miles just to have the thing go up a couple inches, right? But you can lift the whole car, right? So that comes in handy. So that's the principle of hydraulics. If you have a door on a vehicle that's like a hatchback, or the back of like a minivan or something where like it opens up vertically, you probably heard the hissing noise of the hydraulic rams in that door, okay? It'll open and it'll like, psst, or you hear the sliding of the metal cylinders in the hydraulic system. If those hydraulics fail and it's not an electric door to keep it up, right? The door is like heavy, like 100, sometimes 200 pounds of door, right? And when the hydraulics fail and your tiny wife is trapped inside the door, you know exactly how heavy it is. That happened to us once. It was pretty funny. She wasn't hurt, but yeah, it was kind of funny. We're not going to do a quiz. I know we haven't done quizzes in a while, but we don't have time today. So, Archimedes' principle. We're just trying to get through, okay, all of this fluid stuff. Archimedes, famous old Greek guy, figured out lots of stuff. World's first known wardrobe malfunction. You know that story? Yeah, the bathhouse. He discovered Archimedes' principle, and he was so excited he ran out and forgot his toga. Yeah. Running down the street yelling "Eureka!" What's Eureka mean? Like I found it, I discovered. I like to think of it as the Greek version of aha. Yeah. So. That Archimedes screw, Archimedes mirror, all that kind of stuff, okay? What Archimedes did is he didn't discover buoyancy. Buoyancy had been known for a long time. If you jump in a pool, what happens to your weight? Answer is nothing. Gravity's still acting on you. But you're not being held down, are you? As a matter of fact, you kind of feel weightless, don't you? Yeah, what's the force that's pushing you up? There was a sneeze coming.
Oh. It's like, what did I say wrong?
Everything.
Oh.
It's in there. It's coming. You've had your warning. I won't be able to warn you once it comes. So what he discovered was sort of how to figure out what that buoyant force is, okay? Buoyancy, I am not responsible for the English spelling of that word because it's probably a French word anyway. Buoyant or buoyancy means the lifting feature of any fluid. You get into a fluid and it kind of supports you, okay? Think of the buoyant force as the sum of all the normal forces of all the water molecules pushing on you, okay? So what Archimedes discovered, okay, was that, and this is the modern formulation of it, that the buoyant force is equal to the weight of the fluid displaced by an object. You're like, Mr. Balogh, that does not say weight of the fluid displaced by an object. That says rho GV. What's V? Volume. Sorry. Yeah, this is fluid static still. We're not moving anything. Okay. Does depend on which planet you're on and the density. So what's this density? It's the density of the fluid displaced. What does that word displaced mean? Moved out of the way. When you jump in the pool, you displace your volume of water. Okay? The water that you're in had to get pushed out of the way so that you could be there. Okay? So Archimedes, his big aha moment was to link the amount of force that, say, somebody feels when they're in a pool to the weight of the water that got pushed out of the way when they got in the pool. So this volume right here is the volume of the fluid displaced. But how is this a weight? What's weight?
Mass times
mg, right? We've done this before. Okay? Is there another way we can write mass? Think fluids. Instead of mass, we use what? Density. But we don't just do rho g because that wouldn't have units of weight. Okay? Density is equal to mass divided by volume. So mass is equal to density times volume. So if we now stick that up there, and for whatever reason put the g in the middle, okay, you have rho GV is a weight. It's just the weight of something in terms of its density and volume as opposed to its mass. Okay? So Archimedes' principle, this buoyant force, which acts up. Again, think of it like a normal force, right, of when you come into contact with a fluid, okay, acts against the weight of the object. Okay, so what did I just draw right there in the center of the screen?
Free body diagram.
They're back. Right? That is the appropriate emotional response, right? We need to play that clip from, what's that horror movie? They're back. Old 80s horror movie, darn it. Creepy little girl.
That's Shining, isn't
No, it's not The Shining. I can't remember. Anyway, piece of Mr. Bale's childhood forgotten. It's a free body diagram. So what does that mean? Let all the trauma come back. We got to process it. What does it mean? Newton's second law, forces, vector components. Let it out. Don't let it hurt you anymore. Just let it go. Let it out. Okay? Usually, when we're talking about buoyant force, we're referring to objects floating in water. So thankfully, this is a static case, meaning that the acceleration of the object is 0, right? Okay. So we can find the buoyant force acting on objects when they're in water by just using rho GV. But if we want to figure out like how much of an object is above the surface of the water, that comes down to the volume, right, of the object and its density. And you know from experience the kinds of densities that are needed to float things. In order for you throw a rock into a swimming pool, what's it going to do? It's going to why? It was too dense, meaning what? It was denser than water, right? But a basketball thrown in the pool will float. Why? It's less dense than water, right? So it's a comparison to the fluid being displaced that tells you whether or not something's going to sink. If the density of your basketball is half the density of water, then half of its volume will be submerged. If the human body is roughly 95% the density of water, so how much of the human body would be above the surface of the water? 5%. Okay? So 95%, like we are mostly water, right? You are much more important than the description I'm about to give, but you are a bag of salt water, okay? And you've got some bones and muscle and everything else, right? So about 95% the density of water. And when you jump into a pool, on average, a person, right, if they're just floating there, will float with about 5% of their volume above the water, right? Icebergs in salt water, typically they have 90% the density of seawater. So how much of the iceberg is above the water? 10%, right? So that's pretty straightforward, right? But we can use Archimedes' principle to determine like what the actual densities of objects are. That's kind of what Archimedes used it to do, to determine whether or not a crown was made out of gold or not. By the way, that might be apocryphal. We're not actually sure that that actually happened, but we're going to pretend that it did. Okay? But if you've ever heard that story, and we'll do a calculation based on it. But before we get there, let's see if I can show you what's going on with this buoyant force. Did it work? Yeah.
This demonstration will show how the buoyant force on a submerged object is related to the amount of water displaced by the object. This aluminum cylinder and pail hang from a scale, which shows the total weight to be 29 newtons. We'll lower the cylinder into this water container, which has an overflow spout.
Does that guy look like he enjoys his job? Yeah. No smile there.
When the cylinder is submerged, the reading on the scale decreases to 20 newtons. All water displaced by the cylinder will flow into a beaker.
No fun.
If we pour the water that was displaced by the cylinder into the small bucket hanging from the scale, how will the reading change?
Okay, so first of all, when they put this cylinder in, what happened to the reading on the scale? It decreased. Why? The buoyant force is holding it up, right? It decreased by, I think it was 9 newtons. Okay, so where did the 9 newtons go? It went in there. Okay, that's 9 newtons of water sitting right there. So if he takes that jar and he pours it back into the bucket that's hanging on the scale also, what should happen to the reading on the scale? Not decrease, but it should go back up to 29, right? Okay, you're fired if you don't get that in correctly. No, work at it. Work at it. Yeah, I don't know. I see drips. No smiling, this is science.
The scale now reads the same as before the cylinder was lowered into the water. The buoyant force on the cylinder is equal to the weight of the water displaced.
Right? If you can accurately track the amount of water displaced, that whatever the weight of that water is the buoyant force acting on the object.
We'll use these 3 blocks of wood to demonstrate how density affects the depth at which objects float. This block is cut from balsa wood, with a density of about 0.14 grams per cubic centimeter. When placed in water, it floats with only about 1/7 of its volume submerged. This is a block of pine, with a density of about 0.5 grams per cubic centimeter. It floats with about half of its volume submerged. This is a block of ironwood with a density of about 0.9 grams per cubic centimeter. When placed in water, it floats with about 9/10 of its volume submerged.
One of the ways to measure densities of things is to, oh, and by the way, in physics, we use kilograms per cubic meter. Not grams per centimeter. Kilograms per cubic meter. And the the way you convert is multiply by 1,000. Okay? So, we also talk about the specific gravity of something. Specific gravity is a ratio of the density of an object to the density of water. So if the specific gravity is 0.6, then what's its density? It'll be 600 kilograms per cubic meter. So you just multiply. Water is 1,000 kilograms per cubic meter. Just multiply by the specific gravity, you've got the density of the object. Just so when you run across specific gravity, it crops up quite a lot. Okay. I have showed you, through the course of this semester, I've showed you lots of these sort of video clips. Comes from the the Encyclopedia of Video Demonstrations in Physics. Might have gotten that title still mixed up. It's a long title. It's a 24 DVD disc set. Each DVD has about 20 of these clips on it, okay? And I have watched them all. I pick out just the few that are pertinent to what we're doing and are interesting and like actually teach you something. And in every single one of them, I promise you, in every single one, the people doing the experiments are not smiling. They're not having fun. You can tell that the director told them, this is science, this is serious. You will show no emotion. I have to show you this one. I have to show you this one. The actual physics in this one makes absolutely no difference.
We're used to seeing objects floating in large amounts
Yeah,
of
yeah,
water.
big deal. Fine.
But how much water is actually required?
Yeah,
to
get on with
float
it.
an
The answer is not very much.
object? We'll use this wooden block.
Okay,
behind it.
fine. Yes, great.
This container is just barely larger than the block.
Yeah, duh.
And has a small amount of water at the bottom. When the block is placed inside, the small amount of
Okay.
water is enough to float the block.
Watch very carefully.
The amount of water required to float an object is just enough to actually surround.
Yeah, get on with it. We don't care.
the container.
Watch the end of the boat. Watch this end of the boat. Watch.
Size.
Watch it.
A large object, such as this ocean liner, could also float in a small amount of water.
What just happened?
Kill people. Those sea monkeys?
This is what I think happened, okay? I think 24 discs, right? 20 of these little things per, right? I think somebody cracked. Okay? They were holding it in, right? They were holding it in. I kid you not, there is nothing like this anywhere else in the series. Okay? And the graphics department had had enough. And this is how a physics graduate student like expresses their emotional state, right? Like, I don't get it. I mean, I get it, but anyway. It so got through the censors or whatever was going on with this this production. Okay, so had to show that to you. Like I said, the actual physics of that clip stupid, but like, yeah, people falling out. I love it. I absolutely love it. They need to like show videos where physics is more fun. Anyway, okay. I need to do all that. Oh, there we go. So.
Town, perhaps.
Yeah. Let's see if we can use Archimedes' principle to help us figure out the density of an unknown object. Okay. So what do we got? We've got this crown, right? That weighs 300 newtons in air. Okay. Now, a lot of times, what we mean by weighs in air, we're thinking of it being hung by a spring scale. You may have seen these in the supermarket. They're not that common anymore, but like it's got the basket underneath and then the dial switches where you put the, right? Okay. It works for a regular scale too, but generally we're talking about like the tension in a wire that's holding something up, okay? Just so you get an idea. So when we put this thing in a container, right, that's got some fluid, and we kind of measure the tension, right? Now, did the actual weight of the object change? No, like gravity doesn't change, right? What we're talking about is this reading, right? This starts at 300 in air, but then it drops to 200, right, in the fluid. So where did the missing weight go? It went into the buoyant force. So we know here that the buoyant force is 100 newtons, right? Okay. So we also know that the buoyant force has to be equal to rho times g times v. But rho of what and v of what? G is 9.8. We're on the Earth. Volume of displaced fluid. Right? So that's important.
And rho of displaced fluid.
Yeah, both of these are about the displaced fluid, right? So do we know the density of the displaced fluid?
Yeah, 0.8.
It's 700. So the density of water is 1,000 kilograms per cubic meter. For those of you that live in chemistry, a gram per cubic centimeter is the same density in different units. Okay? 1 gram per cubic centimeter, 1,000 kilograms per cubic meter. All right. So if the specific gravity is 0.7 and you multiply that by the density of water, you get 700, right? Okay, so the density is 700, okay, where it's 9.8. And then the volume of the fluid displaced. This is like our one unknown here, isn't it? We know the buoyant force, we know the other things, we know this volume. So we're going to get this volume of fluid displaced. I got it to be 1.46 times 10 to the minus 2 cubic meters. So that's the volume of fluid that got pushed out of the way. What we are trying to find is the density of the object. So if we're going to find the density of the object, what do we need to know? We need to know the mass and the volume. Do we know the mass of the object, by the way?
We can figure it out.
Yeah. It's 300. That looks like 3,000. 300 divided by 9.8, 30.6. Okay. But what's the volume of the object? We know that the volume of the displaced fluid. What's the volume of the object? Why is it the same?
Because it displays nothing.
It's immersed in the fluid. What does immerse mean?
Submerged.
Cover completely. So submerged doesn't necessarily mean completely, but immersed does. However, English is dumb, and we will sometimes say things like partially immersed. And I just want to throttle the person that wrote that, right? Submerged can mean completely or partially, but immersed generally means completely under the fluid. But I'm not responsible for English, thank goodness. So this is going to be 30.6 divided by 1.46 times 10 to the minus 2. Again, this is also equal to the volume of the object because it's immersed. So the density of our object turns out to be 2.1 times 10 to the 3 kilograms per cubic meter, which is pretty close to gold. So this crown made of gold. Or a gold alloy. Most gold in jewelry is not pure gold. It's alloyed with nickel or silver or something else to give it a little bit more rigidity, because gold by itself is a very weak, soft metal. Let's say that you are tired of Comcast's dominance in the internet market in Fresno. And you want to set up some competition. And one of the things that AI tells you to do is to, hey, why not just put a balloon up that has a broadband antenna on it so that you can start serving internet wirelessly to the people of Fresno. And then Comcast can, go take a hike. So I went and I looked for like broadband internet antennas, right? Like the amount of antennas you need to serve, say, 10,000 people, right? Kind of like the kind of thing you see on a cell tower or something like that, okay? How much do those weigh? And I found the mass of it, right? What did it say up there? Okay. 4,000 kilograms for the antenna. By the way, your car is somewhere between 1 and 2,000 kilograms, depending on if it's a sedan or a hatchback or a truck. So this is big, right? So we're talking like a couple Toyota Camrys worth of weight that we got to support. So I went and looked, and I found balloon companies. They exist, okay? And I said, so for a payload of 4,000 kilograms, how big a balloon do you need? And I discovered that the material of the balloon, just the material, is, 600 kilograms? To give you an idea of that material, it's this stuff, okay? This is like a polyethylene plastic, okay? That's like, it's garbage bag material. Do you see how thin this stuff is? 600 kilograms of this. How big is this balloon going to be? Really big, okay? Really big. So we're going to calculate how much helium is required to just float this antenna at ground level here in Fresno, which is about sea level. We're like 400 feet above sea level. And so we're going to find out how many sad clowns there are going to be in Fresno because they don't have any helium for their balloons. Because we're going to use up all the helium in Fresno. How much helium is it going to be? Let's find out. So we're going to use, obviously, we're using Archimedes' principle. Archimedes' principle means that we have to deal with forces. It's a statics problem, meaning that there's no acceleration, which is good. But no matter what else happens, if we add up all the forces on a balloon that's just floating there, what should the net force be? It's got to be 0. So we got to start talking about things that are pushing or pulling on this balloon. I'm going to take the low-hanging fruit there, buoyant force. Right? Helium balloons get pulled up, don't they? Okay. So what's pulling it down? Gravity. But gravity acting on what? So there's the antenna, right? The payload, right? Pulling down on the balloon. It's just the weight of the payload, whatever it is, right? And then there's the weight. I didn't draw these to scale. The mass of the balloon material itself, right? The 600 kilograms of the envelope of the balloon. But that's not it. That's not all. There's one more thing. The weight of what? The helium inside the balloon. Because it has weight too, right? Gravity will pull down on it. And it's not like a little bit. It's going to be a significant amount of helium. So that's usually what people forget, and that's the reason I kind of do this example. It's like when you're being asked to calculate like buoyant forces and all that kind of stuff, don't forget everything has weight. The balloon has weight. Whatever the balloon's attached to has weight. The helium inside the balloon has weight. All of that needs to be countered by the buoyant force in order for a balloon to float. So if you take a helium balloon, you let go, and it goes up, what do you know? First of all, you know you're very sad. Although there's some joy to be had in knowing that you set something free to live its best life. You know that the buoyant force is much bigger than the weight of the balloon, the string, and the helium that's inside of it. If you have a helium balloon left over from a party or something the next day, if you notice them sort of partially floating, like part of the string is on the ground, but it's still floating above, It's like perfectly, like the weight of the string on the ground is supported by the ground, and the balloon doesn't have to support it anymore. It's just perfectly supporting everything, just floating there. All right. So what do we got? What we got is a picture in the wrong spot. Let's move that over there. Need some room. So we're going to add up all the forces here, right? Buoyant going up and all the other things going down. So why the negatives? Going down. And the buoyant force is going up. Okay. We want to know the volume of the balloon. Where's the volume of the balloon hiding? Don't see it yet? Oh, mass of the balloon? All right, let's see here. Buoyant force is what? Density of what?
The displacement of the fluid.
Fluid displaced. By the way, what fluid is being displaced in this example? Air. Times G times volume of what? Fluid displaced. Minus mass of the antenna times G. That's just a number, by the way. Mass of the antenna times G is just a number. It's 4,000 times 9.8. Okay? Minus, do we know the mass of the balloon material?
600.
Yeah, times G. Okay. Do we know the mass of the helium? No. Is there another way we can write the mass of the helium in something that we know? Right? They gave us the density of helium, didn't they? We really don't want to work in mass if we don't know the mass. So I'm going to write this as density helium times G times the volume of the helium. All right. What's, just side note, math, let's clean things up a bit. What's the same in every term? Little g. What did we just do? We just solved the problem for any balloon anywhere in the universe. It's independent of what planet you're on. So if you wanted to fly a balloon in Venus's atmosphere, if you wanted to fly a balloon in Mars's atmosphere, Saturn's atmosphere, Io's atmosphere, anywhere you want to go that has a fluid that can be displaced, we now know the answer. Isn't physics cool? Which chemists can only wish they could do that. All right. Density of the fluid displaced. Do we know that number? Do we know the density of air? It was given. Okay. Volume of air. Do we know what that was? No. Mass of antenna, mass of balloon, minus. Do we know the density of helium? It's in the problem right there. Okay. And do we know the volume of helium? No. There's two unknowns in there. The volume of the fluid displaced and the volume of the helium in the balloon. What do we do about it? You can do that if you want. We've got to get rid of one of them. We either need another equation or a realization about the volume of air displaced by the balloon and the volume of helium in the balloon. They're the same. Why are they the same? Because all balloons are completely immersed in the fluid, aren't they? You're completely immersed in a fluid right now, right? So you are displacing amount of air that's equal to your body minus your lung volume. All right, so we can set the volume of the fluid displaced equal to the volume of the helium. Again, that applies when the object is completely immersed. If they tell you that half the boat is under the water, then your equation has to be volume of fluid equals half volume boat, right? So just look for clues about the relationship between those two things. Both my problems, we've completely immersed the thing. So, all right. So that means I can solve now for volume. Those two volume terms are the same. So I'm going to move these masses over and factor out the volume. Volume and density fluid, density helium, and the fluid this time is air, so I'm going to put that on there, mass or density air. All right, and so this means that my volume is going to be the masses of the payload and the balloon divided by the difference between the density of air and the density of helium, which is 4.14 times 10 to the 3 cubic meters, or 4,000 cubic meters. All right. This wall right here is, we'll round it, it's about 10 meters long. Okay. That ceiling is about 3 meters up. I'm really rounding. Okay. And let's say that this wall is about 20 meters. Okay. So what's the volume of air in this room? 20 times 10 is what? 200. Did I get that right?
Yeah.
Times 3.
600.
600. There's about 500 cubic meters of air in this room right now. How big is our balloon? 4,000 cubic meters. What's 4,000 divided by 500? 8. We need a balloon that has a volume 8 times bigger than this room. They exist. They're used to float experiments and stuntmen, okay, high up in the Earth's atmosphere. This is Felix Baumgartner. He was the first person to ever break the sound barrier without an airplane. He exceeded the speed of sound, went Mach 1.1 or something like that, in free fall, parachuting from the edge of space. Okay? He rode, took 6 hours, he rode up in a gondola. Okay? It was very cold. He did have sort of a spacesuit on, right? Because there's no way to breathe and all that kind of stuff up there. But he rode up to about 120,000 feet, okay? And then jumped out, okay? The balloon that was used to hoist him up there, okay? This is a picture of it rising. Here's the picture of it fully inflated. This is obviously CGI. They're just trying to show you that it was the size, the height of the Statue of Liberty, which means absolutely nothing to us. So basically the height of Golden Gate Bridge, like the span, or the General Sherman Tree, right? Okay. But like, it's a big balloon. And these balloons are used for atmospheric research all the time. Okay? So they exist. There's an industry surrounding them. It's not terribly uncommon. They do take off partially inflated. Why? Remember, they take off looking like they're basically not inflated at all. Pressure's going to be lower up there. It needs to expand, all that kind of stuff. So, yeah, they don't want it to explode. Bernoulli's equation. This is where I'm going to run out of time. And so we'll carry this on Monday. Monday's lab is going to be lecture. I'll finish up chapter 11, and we're going to get started on 12 and 13. Next Tuesday, I will finish up chapter 11. You guys aren't in physics 2B? What's wrong with you? Yeah, next semester. Tuesday, I will finish up, but we will then, on Wednesday, we will kind of finish up. Chapters 12 and 13, I mushed together into one chapter because they really should be one chapter. I cut out a bunch of 13 too because it's just, it's awful. Okay? So, just realize that we're kind of going to be mushing a bunch of stuff together next week. And next week's going to be a heavy, like, get all the lecture out of the way kind of thing so that we can try to enjoy our Thanksgiving holiday. All right, so Bernoulli's equation. This is something, so we just did fluid statics, where the fluids weren't going anywhere. Now we're going to do fluid dynamics. Normally I would start with concept and then lay out the mathematics behind it. I'm going to reverse it this time. Bernoulli's equation says this. That right there is Bernoulli's equation. Without understanding what anything is in there, does it vaguely remind you of something you've already done in this class? What does it feel like or look like? No. Two different points comparing beginning and end, initial and final, setting them equal to each other. Conservation of energy. Right? We're comparing two different things, in this case, two different points in a fluid that's in motion, and we're setting those 2 points equal to each other. In fact, the analogy goes even a little bit further. Look at that second. So the first big P's are pressures, by the way. So this is a continuity. This is a conservation of pressure equation because all the terms have units of pressure. Okay, every single one of these have pascals. Okay, but what does 1/2 rho v squared feel like? It feels like kinetic energy, doesn't it? Because kinetic energy is 1/2 mv squared. We just swapped out the m for rho and we're in fluids, right? And then, even though it's been here the entire lecture today, what does rho gh feel like? Mgh feels like potential energy, doesn't it? Again, these aren't energies, these are pressures.
The V is.
But it's what? No, the v is velocity.
It's velocity.
Yeah, it's the speed that is moving at, little v. Okay. So Bernoulli's equation is kind of like conservation of energy for fluids, but it's not energy. What is it? Pressure, right? It's conservation of pressure, but no textbook will ever say that because I don't know why, but that's what it is, okay? So what does it mean, like 2 points in a fluid, all that kind of stuff? Sort of the generic idea here can be like, you can do all kinds of stuff with this, but you can have a pipe that changes its like cross-sectional area and then maybe goes up to a different height or something like that, okay? So like if we look at the fluid in this pipe at this point compared to this point, we can now set up the equation because the difference in these 2 points, there's a height difference between these 2 points. If we set 0, right, at the lowest point in the problem, we're going to recycle our methodology for conservation of energy, but we're going to apply it to fluids in pipes that are going places, that are flowing. The other equation that comes along with Bernoulli's equation is called the equation of continuity. This is a conservation equation. This is conservation of volume flow rate. Area, meters squared. Velocity, meters per second. So literally, both sides of this equation have units of meters cubed per second. That's a volume flow rate. Like, think of it like gallons per second. It's just we use cubic meters because that's the SI unit, right? So that's like the math, right? But the concept and idea behind Bernoulli's equation is pretty straightforward to understand if you've ever heard of something called a siphon. So a siphon is used to move fluid from one container to another, but there's a trick. In order for the siphon to work, what has to be true?
It has to be higher.
What has to be higher? Something has to be higher, something has to be lower.
It has to be higher than when you put it in.
Yeah. If you want the water to cut, let's say we're draining a swimming pool with a garden hose. Okay? We need that swimming pool to be higher in elevation than the end of the hose where we're draining the water to. There needs to be a gradient in gravity between the two ends. Because if the ends are equal, the water won't flow. The only reason the water will flow is because it's literally running downhill. Okay? So that's what a siphon is. And what we're going to do is we're going to calculate the speed at which the water is going as it exits the hose. If this hose is sitting at a height difference between the surface of the pool and where the end of the water is, we can find out how fast the water is going. We're going to use Bernoulli's equation to do it. We're going to say point number 1 is at the surface of the water. Point number 2 will be here where the water exits the hose. I'm going to put 0 for my height at that lowest point in my problem. And then I'm going to apply Bernoulli's equation. 1/2 rho v1 squared plus rho gh1 p2 plus 1/2 rho v2 squared plus rho gh2. There's Bernoulli's equation. Nothing about the cross-sectional area of the pipes. Don't need the equation of continuity. What's the pressure at point 1 at the surface of the water? There's only one answer. Not 0, because it's not in outer space. It's atmospheric pressure. So whatever the pressure of the atmosphere is on the surface of the water. Okay? What's the pressure on the fluid as it exits the garden hose? Also atmospheric pressure. They're both surrounded by atmospheric pressure, right? So immediately what happens to the two pressures? They're the same, so they cancel each other out. Okay. What about height number 1? What's H1? Yeah, it's H1, whatever it is. Okay. But what's H2? Because that's where we put 0, right? That's nice. All right. What are we looking for? What's our goal? We want V2. We want the speed at point 2. So that means we need to know the speed at point 1. Anybody ever try to drain a large body of water with a garden hose? No? Takes forever. Okay. How fast is the surface of that pool going down compared to the speed at which the water is coming out the end of the hose? Not very fast at all. And in physics, not very fast at all is 0. So we're just going to let V1 be pretty much 0, okay? Because I said so. Because the volume of the pool is so much bigger than the volume of the hose. They do this in water towers, by the way. They just keep filling the water tower. Why do water towers exist? Does anybody know why?
To put the water up high so that,
We'll put it up high. Why?
so that it'll do this,
Do what?
go down,
Why would they want it to go down?
go to houses.
You don't have to put. Why? It's not for water storage.
For water pressure.
It's for water pressure. It's to pressurize the water in the town. If your town has a water tower in it, it's getting its pressure from gravity. If your town does not have a water tower in it, then it means that the pressure is being provided by electric pumps. All right. So if we let that be equal to 0, this goes to 0, doesn't it? And what are we left with? Rho GH equals 1/2 rho V squared. What's the same on both sides? Rho. I'm going to reverse this and solve for V. V squared is equal to 2GH. So V is equal to the square root of 2GH. What just happened? Where have we seen square root of 2GH before? right? It's the speed that a ball is going to have right before it hits the ground if I just drop it. It's the speed that a penguin is going to have as it slides down a ramp. Yeah. It's just conservation of energy gave us square root of 2gh if the initial speed is 0. And what did we just ask the universe? How fast is water going when it falls through a height h? Is it any surprise that we get the same answer? No. When you don't know the answer, square root of 2gh is the answer. We should put that on a t-shirt, right? Because more often than not, it's going to be the answer. It's either that or 42, right? Okay, so this is one of those moments where physicists go, see, we're there. We understand something. Because even though it's a different setup, it's fluids instead of tennis balls, when you ask the same question, how fast is something going if gravity pulls on it? And you get the same answer, pretty sure that we're spot on. I will see you, if not in GRASP, next Tuesday, where I will do a demonstration of Bernoulli's principle, and then we will get on to doing thermodynamics.